Good morning, everybody. So let's start for this next lecture and the last Andrea's lecture on advanced GR.
Okay. So today's topic is the one of asymptotically flat spacetime. And in order to introduce this concept, it is convenient to first recall what is the structure of Minkowski space, because it's the one that we want to mimic in this particular context. So it's something that probably some of you have already seen, but since it is important for the following, let's rederive together what is the Penrose diagram of Minkowski space-time. So this is just Minkowski space in radial coordinates, in spherical coordinates. And here I stress that the range of variables is the usual one, essentially. Okay. Now I want to discuss what is an asymptotically flat spacetime. Means something that approaches Minkowski at infinity, but what does infinity means in the case of Minkowski? And this is something that, as you probably have already encountered, it's something as an information that is efficiently encoded into the notion of Penrose diagram. So I'm going to derive a Penrose diagram of Minkowski spacetime. For those of you that are not familiar with these concepts, what I'm going to do is to try to do a change of coordinates such that I will be able to draw Minkowski spacetime on a blackboard, in a sense that I want to move to a set of coordinates in which the coordinates have a finite range. And on top of this, I also want to do it. I allow myself to work with a non-physical metric that is obtained starting from a Minkowski one by doing a conformal transformation. I will recall what it is. And the final result will be a metric with a finite range of coordinates that I can draw on the blackboard that describes completely the Minkowski spacetime, and in which the causal structure of Minkowski spacetime is preserved, which means that in this metric the light cones will be still at 45 degrees. So I will be able to understand what's the structure, the causal structure of spacetime. And in order to do this, the first step is to introduce some light cone coordinates, retard and advance coordinates, they are called. And for the moment, it's just a change of coordinates, which is convenient for the following. So for the moment, my range of coordinates is still infinite. So I still have to do some manipulations to go towards the end. And these are called null coordinates. After this change of variables, the metric of Minkowski spacetime, so just change variables, can be written in the following form. Okay, so for the moment I haven't done much. It's just a change of coordinates. And just to understand, because these coordinates, we will use an analog of them also for asymptotically flat spacetime, so it is useful to understand what they mean. So suppose that I draw my r and t coordinates. I throw away the angular coordinates on the sphere. So each point on this diagram is actually a two-sphere. And inside here, I can distinguish these are lines with u constant. And the lines with v constants are in colors. Let's see if new one is better. No. Well, whatever. So this is the best that I can do. Sorry, v constant. Okay, I just introduced these coordinates here, and each point on the diagram is a two-sphere. Okay, and now to eventually reach my goal of drawing Minkowski space on the blackboard, I can do the following change of coordinates. I introduce the arc cotangent of u and v, and now with this change of coordinates, I eventually manage to reach my goal, because function tan it's simply something that takes this form. And the same is true here. And that is something important to keep in mind. So it's part of my definition of this stuff that is inherited by the fact that one combination is T minus R and the other combination is T plus R. And once again, I've done a change of coordinates. What is the form of a Minkowski metric in these coordinates? This is cosine square u, cosine square v. Okay, and if I wish, I can also, now I reached essentially my goal, because I have 4 coordinates, all of them have a finite range. So this means that on top of this, I have some coordinates that are just coordinates on a 2-sphere, so I can draw really Minkowski, I can draw R and T, well, the coordinates U and V on the blackboard. They have a finite range. I stay in a finite range, and each point that it will be drawn on the blackboard will be a 2-sphere. And on top of this, I can also make the observation that if I take a metric, a generic metric G, and I introduce a new metric by doing what is called as a Weil rescaling or a conformal transformation. This operation is not gonna changing the form of a light cone, because the light cone are identified by this condition essentially, and this condition is clearly preserved by this type of presentation. So if I take this, I'm not gonna change, I preserve the causal structure of space-time. So this means that instead of studying the metric of Minkowski space in these coordinates, I will just look at the metric after a Weil rescaling, and the metric after a Weil rescaling take the following form. I just rewrite it like this, where I introduced yet another change of coordinates, since this one is not crucial. So I first write, this I do just for convenience, and the new, so the last change of coordinates is just t is equal to, so I undo the definition of, no, I don't have space here. Do we go? Yeah, okay, let me do a big box here. So this is t is equal to v plus u, and r is equal to v minus u. And okay, that's the thing that is really important. It is what is the range of these coordinates. And this is something that you can check. You just perform all the change of coordinates. Okay, and you follow all the chain of transformation that I did, and you arrive up to these transformations here. And what I have obtained as a final result, this unphysical metric, be careful, this is not the Minkowski metric anymore, because I performed a Weil transformations that eliminated essentially this term in front. So this is not anymore Minkowski metric, but has the same structure of Minkowski metric. So I can use it to study the properties of Minkowski space-time. And now let me draw this metric. So what is this metric? Maybe you remember from your classes of GR. So this is the metric of Einstein's static universe. That is a solution that you have of equations of motion of Friedmann-Robertson-Walker equations of motion in presence of dust. You can get, with a cosmological constant, you can get this particular solution. So let me draw it then, just to understand what is the structure that I got. So essentially, in this way, I embedded Minkowski space in Einstein static universe. Why did I embed it? Because Einstein static universe has this metric, but has a different range for the coordinates. So it's very important, the range of the coordinates into this description. And essentially, here I can take the coordinate r that goes around the side of a cylinder, and the coordinate t is going into this direction. And here I have in r, I have a finite range, but I go just from r to pi. And in t, I have to respect this property. So t is an infinite range in the case of Einstein static universe. In this particular case, I know that p at most goes from t equal to pi up to t equal to minus pi. Look at this one, for the maximum values of r. And in the other cases, strings, it becomes smaller. And then essentially what I have here is that I can go along the sides of a cylinder this particular way up to having a point there. Okay, so it's this strip that is going up to a single point there. So maybe that is the way which is more, say, closer to what I introduced here, but maybe what is more familiar to you is the fact that I can just open the cylinder, cut the cylinder and draw it on a plane. And if I draw it on the plane, so this means that is equivalent to what? To something that has this structure here. Okay, before concluding the structure of a triangle and discussing it, just an important remark. Look at the range of coordinates. If we look at the range of coordinates, the boundaries of this region are not part of this unphysical metric. But here I put them at a finite distances. So this corresponds to the point at the boundary, corresponds to the point where you have arc that goes to infinity in the original coordinates. But since now this point's at a finite distance, I can decide to include the boundaries inside the description of the space-time. And this region plus the boundaries is what is called the conformal compactification of space-time. And so in this way, I have my boundary, which is at finite distance, and I can study its properties. And we are going to do it on the triangle where things are a bit easier. So in particular, here there are several regions to distinguish. So this is r equal to 0. And then I have what is called I0. This is called I plus. I minus. This is what is called scri plus, scri minus, and this point here corresponds to r equal to pi. So it's the point on the back of the cylinder in my way of drawing. Maybe I should have drawn in the other direction, but so it's where the points touch together. And here, inside this way of drawing, light cones, I perform just a conformal transformation. So light cones are still at 45 degrees, which means suppose that I have radiation, sort of scattering problems. I have radiation that comes from infinity. The path of a light ray is the following. Yeah, really at this point. So it goes at 45 degrees. Unfortunately, my drawing is not precisely at 45 degrees. So it goes, so this is nothing, so it's just the interior of space-time. If you wish, you can also present the same picture in this particular way. So r equal to 0 is just the center of this sort of cone. So what I'm doing is that if I arrive at r equal to 0, I just proceed and go in the opposite direction. So that when you draw the space in this time correspond to a sort of reflection that I have at the center, which is not, and there is nothing that is reflected. So it's just a schematic way of drawing the Minkowski space-time. So that's our light rays that do this kind of things. And goes, then you see directly the interpretation of this surface. This is what is called future null infinity, correspond at the region in which in a scattering problem there is the incoming radiation. Okay, so I can have a scattering problems in Minkowski spacetime in which I have gravitational radiation or even electromagnetic radiation, because this is just Minkowski spacetime. For the moment, we are not talking about, not yet about asymptotically flat spacetime. Say to simplify, let's take Minkowski with Maxwell, a Maxwell field inside. I have a wave that is coming from infinity, is doing something in the bulk, and then is scattered and arrive to future null infinity. So this is, sorry, past null infinity and future null infinity. Maybe I said the opposite, sorry. So this is the future and this is the past. So from where I arrive and where I go. And these correspond, so the future null infinity correspond to the points in which t is equal to pi minus r, and r is free to vary inside all this range. And they correspond in the original coordinates at the point where r goes to infinity at u fixed. The second information is really important. So you see that what are the differences really how I reach infinity. Because infinity is always at a radial coordinate that grows and go to infinity, but there are different type of infinity in Minkowski space-time. So I can instead look at the lines that are of constant t, for instance, and take this particular form. So this is t equal to constant. And the lines of r equal to constant instead take this form here. So this is r equal to constant in the original coordinates. So you see that in the original coordinates in Minkowski spacetime, a line t equal to constant is just a line. Why it is curved here? It is curved because I'm not talking about Minkowski spacetime. I'm talking about the conformal compactification of Minkowski spacetime. This metric is not Minkowski, and in particular is even curved, I think. Yeah, it's a metric with a curvature. But the causal structure is the same, in the sense that what I'm learning here is that this point here is a point that I can call past time-like infinity, and this is future time-like infinity. What does it mean? If I have any, say, time-like curve starts here, ends there, essentially. So this means that observers or massive bodies move along trajectories that ends at this specific point there. On the other end, this point is space-like infinity. You see that the curve of r equal to constant ends there. And in particular, this is a place where I have to attach any Cauchy surface. A Cauchy surface is a space-like surface, it always ends there. So if I want to have a Cauchy surface, is a slice that ends at I0. Which also explains something that from time to time I may mention. So this a sigma is the fact that say charges like the mass or even say the electric charge. Let's simplify things, because when I'm talking about Minkowski, when I talk about something gravitational, I have in mind the linearized theory. But let's simplify things. Let's talk about Maxwell. So in the case of Maxwell, here is where radiation ends. Here is where radiation comes from, if I have to write scattering problems, and here is where I measure, in a sense, the electric charge. Because the electric charge, if you remember, we obtained by integrating over a Cauchy surface, and then this Cauchy surface was such that the charge was eventually evaluated at the boundary of Cauchy surface, which is precisely there. And We will define charges also on null infinity, but let's discuss it later. And just to conclude the structure of Minkowski spacetime, quickly, before moving to the asymptotically flat spacetimes. There is some subtlety in this way of handling Minkowski spacetime. It is the fact that these points there are really points. They are kind of singular. So while on Scry, at each point of Scry, I have a two-sphere, where the radius of the two-sphere degenerates in future past time like infinity and the space like infinity. But people found a trick. I won't use it in the lectures, but just in this lecture, but just to tell you something. There are some tricks that allow you to solve this problem and really to study more efficiently things that happens close to time-like and to space-like infinity. And the idea is just that you can change coordinates if you want to analyze these places. And you move from a global set of coordinates, which is very convenient, but not very convenient to analyze what's going on in these particular points, to some coordinates that cover only a portion of Minkowski space-time. And in particular, there are two change of coordinates that are useful to this end. One is this one. And with this change of coordinates, the metric become the following. Where I denote collectively something that I will use in the following. So XA are just the angular coordinates. And gamma AB is just the unit metric on the celestials, what is called on the sphere, on this S2 sphere that I have at each point. And another possible set of coordinates of another transformation is a transformation which essentially I flip the role of rho and tau. And in these coordinates, the metric becomes ds square is equal to minus d tau square. Well, let me took the liberty to write it like this. It's exactly, well, no, let me write it like, so it's more symmetric. Okay, so in these coordinates, essentially what I'm doing, the range, these coordinates are not well defined everywhere, but on this diamond, from time to time is also called this stuff, I can divide it like this. And here I have, I can use in this region, this is the set of coordinates that are that I can use, and in the region these are the other ones. So maybe I should have drawn different ways. And these are slicing of constant tau bar, and in this case here I have this type of slicing of constant rho bar. Sorry, not rho bar. And the same in this region, I repeat the same structure. So you see that now in this parametrization, I'm going towards the singular points. They are approximating by surfaces that goes closer and closer and closer, but they go closer to that in a smooth way. And then I can use this kind of parametrization in order to handle what's going to happen in these particular places. So it won't be particularly relevant in the lecture. There are some information that may come from what's going to happen here, but I'm not using it extensively, but just to let you know that you can handle also this singular point. It's just important to slice Minkowski space in a smarter way. And each surface here in this particular slicing is an Euclidean ADS3 ADS3 space, while here I have a slicing in terms of ADS3 surfaces. Okay, so if you encounter something similar, you know what's going on. Okay, so now that is Minkowski spacetime, and one very important feature of Minkowski spacetime is that you have a region where radiation ends. And that was the original motivation in the 60s of Bondi, Metzner, Sachs of defining what is asymptotically flat spacetime. So in modern terms, well, there are even other applications that we can discuss, but for them what was important was to really prove that gravitational radiation exists and it is not an artifact of linearized theory. So I suppose almost for sure in your classes of GR you have seen gravitational radiation as a radiative solution, a wave solution of linearized Einstein equations, but you can do even more. So you can have some radiative solution in the full nonlinear theory. And their goal was to set up a framework in which one can study solutions that, that propagates radiation. And the first things to do is that we want to have something that approach Minkowski spacetime at infinity. So essentially we want to set up to have spacetimes that have the same kind of conformal structure as the one of Minkowski spacetime. In particular, we want to have a Scri plus and a Scri minus also for this more general setup in which I'm working with a class of metric equivalent, non-equivalent class, but really a set of metrics that describe phenomena that involves also radiation. So I want a Scri plus and a Scri minus where my radiation ends and all radiative phenomena take place. And there won't be only radiative phenomena in the sense that I can have a black hole formation, will means that I will have, say, matter that stay somewhere. So starts from here, the black hole creates and have some evolution, but then in this process I can, for instance, create radiation. So then I will have something starting and something will end up at Scri plus. So if I have a boundary condition in such a way that there is nothing at I minus and I plus, I just have a scattering problem. So radiation coming in, radiation coming out. That is really the definition of a scattering problem, but I can have several things together. So I can have static solutions, so I detect charges there, and other type of situations into the game. So for what I will do today, I will focus mainly on scattering problems. So I ignore what is going to happen here and there, but you can also involve them, include them in this. So these kind of situations are anyway included into the framework that I'm going to develop. So if you want to define what is an asymptotically flat spacetime, which is a metric that mimic this Penrose diagram there is one strategy that is to use the same technique. So you work directly at the level of conformal compactification, and then you define a class of metric in a conformal compactification that have some nice properties, such that at the end you have something that has more or less the same property as this conformal diagram. That is not the route that I'm going to follow. That is the approach that has been developed by Penrose and collaborators, and has the advantage of being an approach which is completely coordinate-free. So it's very elegant, but maybe a bit more involved, and I will use a different approach that will allow me to arrive directly to the core of the problem, and it is the one of setting just a gauge and fixing some boundary conditions. So I have to define what are the metrics that are asymptotically flat. The easiest way is to say, okay, these are all the metrics that approach the metric of Minkowski spacetime in a specific way. And this is also closer to the approach that you have followed in the previous lectures, in which we were setting some boundary conditions and trying to understand what are the residual symmetries, what are the symmetries of a problem, and so on and so forth. And so let's then begin by setting this setup. And there are several different ways of defining an asymptotically flat spacetime, all equivalent, and they correspond to different gauges, essentially. So I will define for you one an approach which is the one that has been followed in, I think, 62. by Bondi and collaborators, and is just setting up a preferred coordinate system in which it's easy to understand what is an asymptotically flat space-time. And in order to do this, what I do is to start from a family of null hypersurfaces which are parameterized by a certain parameter, u, that I consider constant. So this is a null hypersurface. So this should be 45 degrees. So say that this one is u equal u0 and this is u equal u1. So I have this family of null surfaces that I use to foliate, in a sense, my space-time. So since these surfaces are null, then their normal vector is null by definition. So a null surface is a surface that has a null normal vector. Null surfaces are a kind of strange beast because they also, the tangent vectors are null, but say to begin with, the important things is that for the moment, for us, the important things is that their null vector, their normal vector is null. Okay, so the surfaces are just fixed by surfaces at which u is constant, so they are really labeled by the coordinate u, and then the normal vector is simply something that I can write in this particular way. But since this normal vector is null, so which means that this is 0 must be equal to n mu, or if you wish, well, I can write it here. What I'm discovering is that in this, if I choose this way of foliating space-time, GUU must be equal to 0. And so this is a gauge fixing condition. I could have said it from the very beginning. Now I'm deriving the constraints that I have on the metric in sort of constructive way, but just by presenting to you a particular coordinate system that I'm defining in this particular way. So that is the first condition that I impose, which is not imposed just by chance, but is the consequence of the fact that u is a parameter that parameterizes the family of null surfaces. And then I can introduce some angular coordinates. And these angular coordinates are such that they are constant along null rays. Being constant along null rays just means this condition, and this condition of being, so essentially the angular coordinates are the coordinates that are parameterizing these coordinates here, and I'm missing one dimension clearly because I cannot draw it on the blackboard. And this condition here means that G mu nu d nu, which is just the definition of my n mu, u, no, that is, well, let's do it like this, xa is equal to 0, but this term here is just g ua. So I gain another gauge fixing condition coming out from this. And eventually, the other one, what I missed to define, is a coordinate which is a radial coordinate. So now is that these kind of conditions are common to several gauges. Now there is a difference. The historical one of Bondi and Sachs is a bit weird. There are some choices that are maybe more smarter, but this is the one that you find more often in the literature, so I stick to the definition of Bondi and company, and the definition is that is a sort of areal distance that is measuring the distance depending on the area of the surface that I have here, And this is the condition that they imposed. So there are other parameterization like the Newman-Unti gauge. In the Newman-Unti gauge, the radial distance is kind of smarter because it's an affine parameter along the surfaces of at U constant. And this brings to some other simplifications that are used in other contexts, but most of the basic references about what is an asymptotic spacetime use just the original Bondi-Sachs coordinates. These are called also Bondi-Sachs coordinates. So I decided to follow Bondi's presentation of now to set up this coordinate system. Why? Because like this you understand what is the role of such these coordinates. So that we are really parameterizing these kind of null surfaces. But if we take a perspective that I mentioned maybe a little bit en passant during the lectures, you see that here what I did is just a gauge fixing. Good question. So maybe I think that it is a power 4 if you write it like this. But then maybe there was a typo in the source because there I'm pretty sure that is a power 4 if you write it like this. Now, is this meaning that this must be a power 4 or a power 2? Yeah, so it gets another, yes, an R4. Yeah, that's true, because the same R4 that I have there, but even if it is put like, yeah, I think. Yes, yeah, probably, exactly. But let's say this should be the safest way of putting where, yeah, sorry, right. But yeah, okay, thanks. Okay, but say, well, Carlo already anticipated what, in practice, what this condition is telling us is that we will have a GAB, where A and B are the indices that are there, that starts like R square, the metric, the unique metric on the two sphere, plus a subleading term. So it will be even more manifest. So that is the constructive way, but we can see it from the viewpoint of the gauge fixing. And from the viewpoint of the gauge fixing, I was saying, so let me write what we got for the metric eventually. So the metric after we have done there, so here I derived this condition for the inverse metric, but we can just transform it into the coordinates of the metric, and the final result is that we have an object like this. So this means that the condition that I have imposed in this thing, we can look at them, what is missing. This I don't have. This I don't have as well. And then I have this constraint on the metric. Let's count how many conditions I imposed. This is clearly one. Remember that XA has angular coordinates, so it's taking two values, 1 and 2. So we have 3 conditions, plus 1, 4. So it's similar to what I mentioned that we have done in the Pfefferman-Graham gauge in ADS3. So we used essentially our freedom of performing gauge transformations, parameterized by a vector that has 4 components in 4D to impose some conditions. So this is just a gauge fixing. So you can even present it like this, but with this construction you understand what is the meaning of the coordinates. But I just did a gauge fixing. The fact that I did a gauge fixing, what does it mean? But for a moment I haven't done anything. I just set up a coordinate system that I can use to describe whatever metric. So I haven't defined for you still what is an asymptotically flat spacetime. I just any metric that I like, solving or not solving Einstein equations can be written at least locally in these coordinates. And the idea is that this is something that will be true towards the boundary. Of course, there could be global problems. I may not be able to use this patch everywhere to have a global solution, but at least what is clear is that locally I can always, in a patch, I can always pick up this coordinate system. And the fact that I have these null surfaces is clear. It anticipates that I want to use this coordinate system, this patch, just to use as a patch close to null infinity, essentially. And okay. So now the next goal is that I wish to, so this is just, say, yeah, it's again, these are just the Bondi Sachs coordinates. And this is just a gauge fixing coordinates. And I stress that this is only gauge fixing. Okay, super. Now, what I want to do, I want at least that the limit for r that going to infinity to ds square is equal at ds square of Minkowski. So, questions? No. Okay, so that's, I want to approach Minkowski at large distances. But the problem is that this is not enough to really define what I want, so I have to tell you how I approach Minkowski, or if you wish, how fast the components of a metric goes to 0 or goes to the value which is the value that they have that they take in Minkowski. And why this is important? Because it's defining my space, and how these conditions are settled. Well, there is one important condition. I want to have the solutions that I like and love. So if my set of boundary conditions do not contain the solutions that I want to have in my space of solution, it's clearly crap. And I can generalize them up to the point to have charges that are finite. So that is the other requirement that is used. There are some subtleties there, but well, I will comment more later, but really the setup in the 60s, it was, I want the solutions that I know, and I have to have finite charges. So what are the solutions that you want to have? Well, for instance, you want to have some radiative solutions that are inside, so you want to have radiations that arrive up to infinity, and you want, say, to have your Schwarzschild solution inside. Unfortunately, seeing if the Schwarzschild solution fits is maybe not so evident because it's a different set of coordinates. These are not Schwarzschild coordinates, so you have to do the effort of making the change of coordinates to go there. But these people back then were very serious, and so they checked that the boundary conditions that I'm giving you are satisfactory in the sense that they contain all the solutions that we want to describe in GR, and what has been settled in 62 didn't change essentially over the year. Well, apart from some formal developments that we are going to discussing later. But the basic setup is essentially the same. And so now the fall off, say Bondi fall off, which means the actual boundary conditions are the following. So for what concern GUU must start with a -1 because I didn't. Sorry, that is a bit stupid, but I should write for you the metric of Minkowski that I want to it in these coordinates, sorry. And the metric of Minkowski is du square in these coordinates du dr plus r square gamma ab dxa and dxb. And let me stress again that this is the metric of Minkowski. Okay, that's the metric of Minkowski space. That's once again is the unit, the round, the metric that gives to the round sphere a metric of radius 1, a unit radius round sphere. And to fix the ideas, essentially gamma AB, you can choose coordinates. In the usual coordinates is just one. If I use the usual coordinate theta and phi, the usual polar coordinates theta and phi on the sphere. Clearly, I can change coordinates. In a common parametrization in most of the literature uses the stereographic projection in such a way to have complex coordinates z and z bar, but just to fix the ideas, that is more than enough. And so let's look at the boundary conditions that have been found. So here is the metric that is fixed by Minkowski spacetime, plus the correction should be of order r to the minus 1. What happens if I have something that goes to 0 slower, say that I put, well, if I have something, this particular case is the minimal things that I can do in a sense, no? Because I want to have something that goes to 0 when we take the limit, and it's kind of sufficient. Then we have G UR is equal to minus 1 plus order r to the minus 2. Here you see that instead the situation is a bit different, because a priori I could have the term r to the minus 1. And of course, if all my solution fits within this class of boundary conditions, they fit also if I put a term of the type r minus 1. But if I put the terms of the type r to the minus 1, I have some divergences in the charges associated to these. So I have to discard this kind of behavior, or do something more complicated to try to see if I can give a meaning also to this type of behavior. And the other ones are GUA is say if the correction is r to the minus 1, the charges diverges. So, and then say at phase value, they diverge on the nose, the charges that I define for you diverge. Then you can play with these ambiguities and try to do more complicated stuff, but on the nose they diverge. So then discarded non-physical. So it's like, suppose that you have a condition like this, it will be, I don't know, something like having some unphysical distribution of matter that arrive to infinity. So it's not, it's not the same as the energy condition or this kind of stuff, but in general relativity, you have to put some condition into the game that tells you what is the class of solution that you find acceptable. So these one are discarded, and in this particular case, just because the charges diverge. And then we have GAB. So as anticipated, somehow the condition that I set on the radial derivative was just to get this condition plus possible corrections on the other end. I also have some terms which are of order R. Okay, and these boundary conditions are specific of this particular parametrization. No? I can take another gauge, say Newman-Unti, same strategy, I fix completely the gauge, but the type of boundary condition or things that I settle is different. Then this one maybe I keep. Okay, so now I fix the gauge and I define my fall-off. But now what's the next step that I have to do? I want to understand what is the space of solution of my theory. So I want to classify this fall-off apply also to metric that are off shell, not necessarily for metric that solve Einstein equations. So next step, I take all these conditions that I set up, so the one that's set to 0, some specific components inside there, they fall off. I take all this beast and I throw it inside the Einstein equation and I see what I get. And what we get, so I won't do the computation directly because maybe you can do for the first order, but it's, say, a certain amount of computation. I already give you the solution. So now I'm gonna write for you what is the on-shell form of a metric that satisfy the Bondi the Bondi with fall-offs, essentially. Of course, I'm not gonna write completely the metric because I should go, the expansion doesn't stop. So it will be an expansion in powers of R that goes up to infinity. And this is another proviso, so I will look at the metric in an expansion of powers of R. So I will write the metric as a polynomial of R. So there is the assumption that close to infinity, all solution can be written as polynomials of R. So that's, there is a debate about what one can do, if it is physically capture all solutions or not. And I would say that there is a certain agreement in literature now that what I'm doing here is good enough to discuss the asymptotic symmetries, but if I want to really describe a full space or solution of general relativity, I should also insert some terms in log of R. They won't be there today because they just bring some complications that are irrelevant for the basic setup, but well, I mentioned to you that you should also add some terms in log of R that still respect these boundary conditions, because I just told you the behavior, but I haven't told you what is the functional dependence on R. So the standard assumption is that if you do a expansion in powers of R close to the boundary, you capture everything that you want inside your space of solution, aside from some subtleties related to the logarithmic term. But if I assume an expansion in powers of R, and I throw this boundary condition inside the metric, what I get is the following. So I have, of course, the metric of Minkowski space plus corrections. And let's write piece after piece the correction. So first correction is a term of order R. So the only one that allows terms of order R is GIB. And so the term of order R is a correction that stays there in the metric, and I get a function of this type. This function is almost completely free. There is just a small constraint that I'm going to discuss in a while. But for the rest is a function, well, let me even stress it. So a priori, the fact that I obtain something that doesn't satisfy any differential constraints is not obvious, because the Einstein equations are differential equations. But somehow our differential equation, they must have some free data somewhere. Usually we are used to set free data on a Cauchy surface, the white line here. In this particular case, somehow I'm changing the framework, and I'm setting the analog of the independent data of my space of solution at scry, at null infinity. So there will be a certain number of functions that I have to specify at null infinity in such a way to characterize the solution inside the bulk, I would say, so inside the interior of space-time. And since this is a very strange initial value problems, because I'm setting my initial values at a null surface, maybe the distribution of function is not what you are used or expected to see if you are on a Cauchy surface. That is kind of a difference. In ADS is much simpler. So you have boundary data on the boundary of a cylinder, and where the boundary data takes a while, it's much easier to to count them in a sense, because it's very similar. A space like infinity, so a time-like surface or a space-like surface have a kind of initial value problems that are very similar. So in ADS, I can either solve equations, Einstein equations as time evolution or as a radial evolution. Here I'm trying to solve a sort of null evolution, which makes the things much more complicated in a sense. But that is the thing. So I have to characterize the space of solution, which means certain free data on scry, essentially. And when I go next order is the linear order. And at the linear order, I don't get anything new, because these are just terms that depends on what I already introduced at the previous order. So this tensor C, well, let me call it C square in the following, just to simplify my life. Okay, so Einstein equations, you do a radial expansion of Einstein equation, you expand them in powers of R, and typically these equations, so some equations are automatically solved, thanks to the fact that I fix the gauge, and the other equation typically are recursive equation in R. They told you that what you have at order R is related to what you have at order R plus R minus 1, or 1 over R to an X power. So it's typical with recursive structure, and this recursive structure is reflected into the fact that as I introduce some free data at the boundary, and these free data, well, they appear at the subleading orders, and they typically appear here. You see already something which is important, well, in quadratic, cubic, and higher combination, because Einstein equations are non-linear. So if I would have solved a linearized Einstein equation in the same set of coordinates, this term I wouldn't have seen this one, but for the rest, nothing would have changed. So the free data are the same in the linearized or in the nonlinear one. But in the nonlinear one, we gain this type of terms. And now let's go one other order next, because this is important. And the next order, there is a new function that appears. For the moment I'm writing it, this new function, in a second I will write the condition that satisfies, but this one is not free, so it's satisfying a differential equation in U. Well, this means that there are some free data inside, but it's not a full U dependence. And that will allow us to understand really what is the meaning of this kind of stuff. And then here I have another free function entering. Well, not completely free function, but another independent function enter into the game. M I already included, so I don't put it in blue anymore. Minus 1/8 the AC square. And now what is missing is this order there, because it was R minus 2. So let's check if at the order R minus 2 there is something new, but there is nothing new in the sense that I just get and this dot 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 means subleading orders. Or let me even be more precise, I can. Yeah, let me say dot dot dot, because I haven't checked. I suppose that there are also some orders in the other coordinates. So there are even terms which are subleading with respect to the one that I already in the other coordinates, dxa and dxa. So let's write it like this. So now an important thing is that I have these blue functions here that are the ones that are the most important one to discuss asymptotic symmetries and the series of effects like memory effects and so on in gravity. But an important thing to remember is that here there are other free data on the boundary that are hidden inside the subleading orders. So in ADS is not the case. In ADS, I don't know if you already encountered this or you already heard about this. So the boundary data are a boundary metric and the boundary energy momentum tensor. That's it. So they appear at a certain order in the radial expansion of the metric. Once you fix these two guys, the full space of solution is determined, which means that in the subleading order, you just have crazy complicated combination of derivative of a boundary metric that acts on the boundary metric either, or so combination of boundary metric and derivative of energy momentum tensor. Instead here, you have new stuff that appears at each order. What is the interpretation of this stuff that appear at this order? So they are related to the multipoles of your solution. So in a sense, if you have a static solution, sorry, not a static, spherically symmetric solution, everything is determined just by the mass. You just measure the mass. But suppose that you have, say, something which is really like a sphere with mountains and valleys like Earth. If you want to describe it from infinity, so you have to measure the multipoles of this expansion, which is similar to what you have in electromagnetism. So you have to capture the so the multipoles are the way at infinity to reconstruct the characteristic of the solutions. And the multipoles are not included in this solution here, but they have some contributions that arrive there. In practice, it's just that the structure of Einstein equations with particular gauge is such that the Einstein equation leaves you the freedom of some free function of the angular coordinates. You don't have any more free functions of u. This is gone. All free functions of u is written explicitly on the blackboard, and actually we're gonna see in a while that it's just here. But there are an infinite number of just free functions of the angular coordinates that are necessary to specify your solution. So if you have to specify the Schwarzschild solution in this coordinate, at some point you stop, but you may have a crazier solution that requires to have all these multipoles switched on. Okay. Yes, so the missing piece of information here is what happens. So I keep the Penrose diagram, but I maybe remove the cylinder. So what I have written on the blackboard there does not include all the information that I extract from Einstein equations, because Einstein equations at these orders already also give me some additional information. And in particular, they tell me that M is satisfying a differential equation in U. And N is also satisfying a differential equation in U. Well, it's a bit long, so I don't waste the time to write it, but the important thing is that there is a differential equation in U. Another important, well, not important, but you should have complained, so nobody asked me what is D. So D is just the covariant derivative with respect to the to the metric on the unit sphere gamma AB. So just you have your gamma AB, you compute the Christoffel symbol associated to this gamma AB, and you define a covariant derivative. This is the symbol D. So if I forget to introduce something, please stop me and ask. But that's now I think that with this I should have explained all the notation that I introduced, hopefully, and why these equations, additional equations that I get are important, because they are telling me that the U dependence of M is fixed and the U dependence of N is fixed. So the only object that has a U dependence is really CAB, that has a true U dependence. And this different situation is related to the interpretation of these terms. So the first term here, M of U XA. So I said that there is no U dependence, but I put U. Once again, no U dependence doesn't mean that there is no dependence on U that is constant in U, means that the dependence in U is fixed. It's a fixed function of U that it depends. Yes, you should have complained. There is another symbol that I haven't defined here. NAB, exactly. Please complain. So because if I forget, so real. Good. So NAB is this one. It's just defined like this. Okay. So now you see that there is no independent objects that come inside, but it's just this object here. And now let me give you the names of these objects. So this is the Bondi mass aspect. This is the angular momentum aspect. And this is called Bondi news. Okay, so let's see, in your opinion, where the information about gravitational radiation will be encoded, in which of these functions? Sorry? In? I haven't heard. NAB, exactly. And why? Well, not because... Yeah, no. The important things of NAB. It was a good attempt. Is the fact that there is an arbitrary dependence on U, and that is really crucial because if I want to send radiation on null infinity, well, I want to be able to send whatever wave packet I wish. So this means that I can have a wave packet that arrives there at these U coordinates, then stops, and on another one that arrives there and then stops. So I must be able to freely choose my data at U. So different U dependence means different radiation, different combination of wave packets that reach infinity. And once my radiation that reach infinity is fixed, then these other two charges are fixed, and then it's pretty obvious what they do. So the Bondi mass aspect is encoding information about the total energy of the system, and the angular momentum aspect is encoding information about the angular momentum of the system in a very subtle way. So I'm not going to discuss much about the angular momentum because it's subtle how to define the angular momentum. But last piece of information.
So, independence of the mass aspect or the angular momentum aspect are fixed in terms of the news.
In terms of the news, yes, that is a very good point because the news enter here. So here is manifest. So is depending on what you send at infinity, you have a different dependence on a mass, but the dependence is fixed by these independent data that are there.
I mean, in principle, just as a mathematical problem, couldn't you transport the arbitrary dependence on U on M and then derive it?
In other gauges, yes. In the sense, for instance, in human UNTI, you have a structure which is similar. So you have, say, a GAB or a HAB here, but the information around about the gravitational radiation is scattered everywhere. Yeah, maybe this is the point. Okay, so I said at some point the Newman UNT is a very cool gauge because you have that R is an affine null parameter along with surfaces. But then the problem of that is the advantage of Bondi. That's a good remark. But in Bondi, it's much easier to understand who is who. Inside this definition. While in human UNTI, you can have a solution with radiation that has the analog of a news that is equal to 0, while everything is encoded into the GUU components or something like that. It's a bit more messed up. Like here, indeed, it's kind of more transparent.
If you could the flux of energy flowing to sky in human UNTI, you find a combination of different functions.
Yes, I guess. And I think that you have Robinson-Trautmann that has no, the analog of the analog of a Bondi shear. So the piece that stays in GAB is 0 for Robinson-Trautmann. This is a solution that has radiation. So different gauges have different features, but in this particular case, there is only, all the dependence on U is sitting there, so it's clear that it's there. Okay, I try to speed up. I promise to give you a super translation, so I speed up. But before speeding up, there is one remark which is important that I cannot not do, and it is a condition about the Bondi news. So the Bondi mass aspect, and its dependence in U is fixed. So with a Bondi mass aspect, you can write an object. Where do I go? So maybe here. Yeah, well, this one anyway, I haven't written anything, it's not so important. So I can define an object which is just an integral over the sphere of this object there. So, and this object is what is called the Bondi mass. I just integrated over the sphere, the Bondi mass aspect. And this object satisfies two very nice properties. So the first one is that the limit for u that goes to minus infinity of m of u is the ADM mass. Which means that if you go, going to minus infinity, you go to this point there, and this means that this mass there is measuring really the mass, what we would have, what you define as a mass usually in general relativity. But the other nice property is that m of u is a monotonically decreasing function. And this has been proven rigorously with this set of definitions. And why it makes sense that it's a monotonically decreasing function? Because in this problem, I have radiation that reaches Scry, so that is exiting from space-time. So my isolated system is losing mass because it's radiating away mass and angular momentum, and in particular mass, essentially, radiating away energy. So is mass must decrease. The total energy of my system must decrease because part of the energy is radiated away. So in this sense, this is really the object that is measuring the mass. It's a good definition. And here we see a case in which the fact that some charges, so this charge here is not conserved, is not a mathematically craziness, but it's something that we need to describe a physical situation, because here I must have something which is not conserved, because I'm radiating away part of the energy of my system, and then the charge cannot be conserved on Scry. So it must be conserved maybe here, because that is just the mass, which is the static mass that is measuring something at the beginning, but on Scry, I radiate away, it cannot be. If I would have defined a mass which was constant, it would have been a mistake, essentially. So that's it. It makes a lot of sense. And now, okay, quickly. So, yes, there is another information that I haven't told you. Sorry, let's say, what are the initial data at the boundary, just to summarize. Well, at Scry plus, say. Of course, I can do the same also for Scry minus. It will be completely symmetric, the situation. And the first things that I haven't, that I forgot to tell you is that CAB, well, it is manifestly symmetric by the way it enters into the metric, but there is also an additional condition. So this guy is symmetric, and the other condition is that it is traceless. So it is an arbitrary tensor, but a traceless one. That is important. So it is a 2x2 matrix, symmetric and traceless. It contains two free data. So it contains two arbitrary functions of u. What are these two arbitrary functions of u? Are the two polarization of the gravitons that arrive to infinity. So it's correct. It's consistent with the fact that, once again, thanks to Dario's question, so we go back to the fact that this parametrization is the most natural one. So all radiation is sitting there, because it is parameterized by that place. And why I introduced this news, this Bondi news, because actually the radiation is actually encoded in the Bondi news, but the Bondi news as a derivative in u is killing a possible zero mode of this term. But there is a zero mode that survives in the sense that I can rewrite CAB is an SO3 tensor because it is traceless. I can rewrite it in this particular way. So where you see manifestly the 2 degrees of freedom. And if I look at the part which is constant, no dependency in U, these equations of motion, this differential equation that I've written there, brings some constraints on this stuff. So it's a long expression, doesn't make sense that I copy it on the blackboard, but the condition is that for the U-independent part, this guy is not there. And then summarizing, what are called sometimes characteristic data at the boundary are what? So I have this, the constant part of this guy, defined at scri plus or minus, so this is minus scri plus minus means the point where at u equal to minus infinity or scri plus. So if I have objects that have a dependency in u that is fixed, I can fix some initial data in one point, and the natural place where to fix it is really at I0, a space like infinity, where I can match with the ADM quantities. So this is the thing that is a bit subtle because it depends on some equations that I haven't written in detail. But one thing that is clear is that another data that I can give independently is this one. And it's just the ADM mass, essentially. I fix the ADM mass of the system, and then depending on which radiation I put inside my system, I can get or not, I can get a certain evolution in U of this quantity. The other data similarly is this one. And then the other things that I can choose instead completely arbitrarily is this guy here. So this is what Einstein equations tell me. I may have to add some additional conditions because I have to do maybe some integration in U as well. And actually there is a condition on this guy here that cannot be derived just by solving Einstein equation, but it's part of putting, in a sense, my setting up my problem. That is a subtlety that it will be completely relevant in the following. But here you have some certain dependence in U as well for this particular field, which means that you can have radiation also very close to space like infinity, but it cannot go too fast, so you must have some of it in the very far past, for instance, or in the very far future, you almost have no radiation at all, and or it just have to go down. So if you have radiation that has compact support, this condition is clearly satisfied. So if you do not have radiation in the far future or in the far past, it's perfectly fine. And these are the conditions that have been studied by Christodoulou and Kleinerman. But so that is a kind of more advanced topic. And while there is a dot, dot, dot here, the dot, dot, dot here correspond to the dots there, to the multiples that I still have to specify. I think it's always 0. That will be relevant for you. Because it comes from the conditions that you have there. At least that is the claim. So it's only, you have only one super translation mode, not two. Yes. No, well, for generic U, no, that's true. So that's, I was insisting that it's just the part which is, say, at the U-independent part. Because the generic U dependence is encoded inside here. So I know that is a bit confusing because here you have a C and here you have N, but since N is the du of Xi, essentially it's taking all the, so is the du of C. Exactly. With the exception of a constant part in U, and the constant part in U is not there. Essentially, that is the claim. While this one guy here, well, looks, say, okay, who cares? We have a function more. We have a lot of function there, but I guess it will be important for Carlo because this is related to memory effects that will be discussed later during the course. So that's it's something that you see macroscopically leads to some effects that are not static effects related to multiple expansion. So this is why it's I put it on the blackboard. Okay, so I think I said what I wanted to say here. So is it clear? So what I set up is the space of solution that satisfies the fall-off condition that I given, so my boundary condition. So you fix boundary condition, you reconstruct the space of solution that satisfies them, and we commented that each piece in this space of solution has a certain interpretation. Now, next step is seeing what are the asymptotic symmetries and see effectively what I obtain. So in order to discuss asymptotic symmetries, the thing that I have to do is to discuss what are the residual symmetries of my boundary condition and then see what are the effect on the characteristic data at the boundary. So I have to look at diffeomorphism that preserve my boundary condition. And I will do this operation in two steps. First of all, I can classify the diffeomorphism that preserve my gauge fixing. So that will be true also for solutions that are not asymptotically flat. And preserving my gauge fixing means that I impose the condition that GRR is equal to 0. This means that if I act with a diffeomorphism, this condition must be preserved. And is this one? Then the other condition that I imposed was that GRA is equal to 0. And then the last condition is that LXI of TR of the determinant of GA B divided by R squared, R4, sorry, is equal to 0. And these conditions, again, I don't have time to do the computation with you, but that's solving the Einstein equation is tough. This one is a computation that I really suggest you to try because it's much easier. So the first condition, this condition here tells me that Cu is equal to F. So that is probably the simplest one to do. How do you do this? So for instance, you write explicitly the Lie derivative of this guy, and you see that the solution is only that one. So maybe, well, let's see. So if I have time, we'll do on the blackboard later, but let me write the result. But it's really an exercise that you can do. So it's not something that you have to do with a computer or it's a complicated stuff. So here what is important is that here I don't have terms, so I'm assuming an expansion in powers of R also for the gauge parameters, for the vectors. And here the things that I found is that a priori, but I haven't finished. I only looked for the guys that satisfy the gauge fixing, and I found two arbitrary functions of U and A, one there and one there. No, sorry, this one, yeah, I think it's still with a dependency in U at this stage. I have to check, but okay, but the two of them, and you see that the rest is determined as a function of Y and F, and the same is true for the subleading orders. Now, if you wish, you can be even more brave and write the subleading order as an integral over R of a certain combination, but it's not, that is irrelevant for what I want to do. Sorry? Yes, this one, yes. This one you are asking? Yes, thank you. It's just, this sphere is a Riemannian, not a Riemannian, it's a Euclidean manifold, it's just a two-sphere, it's just the Laplacian on the sphere, this guy.
I'm sorry. The second term in the CA, 1 over R, the
yes.
comes from preserving the gauge.
From preserving the gauge, yes. No, as far as I know, should come, if I put it correctly, should come from there. Yeah. But yeah, it's just for a matter of time, but we could do together. No, we can probably we won't do together, but you can check. I think it's coming from preserving the gauge if I didn't do any mistake. And now we have to impose the boundary. What are the additional conditions that are imposed, that are brought by the fact of satisfying the boundary conditions? These are my boundary conditions. Yeah, maybe for the previous question, so okay, I have to recheck the notes that I don't have here, but it makes sense that it comes from preserving the boundary conditions, because otherwise you will have another function that is there, while the fall-off are just putting constraints on the function that I have into the game. So I'm pretty sure that there are no other functions no other free functions into the guys that are set to 0, I think. They may be there, so there are other independent stuff if you allow for a conformal factor in the boundary metric, but I think that there are not. But okay, we can check later. But you got the spirit, so that some conditions come from one set of conditions and another comes from the other one. So here, just to be concrete, I rewrote the conditions that I have written before, no, because it's just this guy's order R, and so on and so forth. Yeah, and now let's see what's going on. So there are two of these equations that are more useful than the other ones. So this one and this one. And the first condition is imposing a differential condition. Well, let me write it explicitly with a du of f is equal to, no, why 3 functions? Ya are 2 functions, yes. F is a scalar. For the moment, you have a scalar and a vector with this thing here. And I get this condition. What does it mean that I get this condition? Well, let me do it more explicitly. So it's just the fact that L xi of GUR, it must be ordered to the power R minus 2. So this is as something that, well, that's I haven't checked, but I think it's R to the minus 1. And then you have this term here inside. So this term here, I don't care. They preserve the boundary condition. They can do whatever they wish, but this one is not compatible with the boundary condition, so I have to set it to 0. But setting it to 0 means that if I have to impose that this guy is equal to 0, this is implying that f is not an arbitrary function of u, in the sense that f u x a is something that I can write as dxa plus u divided by 2 dA ya. But I still have an arbitrary function of the angles that survives. And then I can look at the other one. And the other one, which is relevant, is this one. And yeah, I think it's R. Let's I haven't checked to remember. Is it R? The power? I think it goes on. Yeah, R square with the beginning. Well, let me say that eventually, so because you have two orders that enter into the game, there is the R square and the order R that combine between themselves. You have to put both of them to 0, where it is. No. Well, eventually the condition that you get in order to respect these boundary conditions that we have here is the following one. And this condition, maybe you already have encountered, is the conformal killing vector equation on the sphere. So this means that Y with this boundary condition is not an arbitrary vector, but is a conformal killing vector on the sphere. And in particular, how many independent solution has this equation here? It has 6 independent solution, and 6 is the dimension of the Lorentz group. So this means that the solutions, well, it has 6 globally defined solutions, and these solutions correspond to Lorentz transformations. So Y encodes the possibility to perform Lorentz transformations at infinity. So why are there Lorentz transformations that pops up into the game? If you think at what I have done, if I would have put 0 everywhere here, I would have looked at the exact killing vector of the background. So in particular, putting 0 everywhere means that what I'm doing is just solving a very simple problem, classifying the killing vectors of Minkowski space in a crappy coordinate system. So here the solution seems weird, but eventually I'm just rewriting, if I put 0, not in this particular case, but if I put 0, I'm just rewriting something that the final result must be mu, which is equal to a certain constant, plus a, well, plus a term which is mu nu x nu. Okay, and where here I have a certain number of constants inside the game. So this is just a solution of the killing equation of Minkowski spacetime. Here is, but there is in Cartesian coordinates. Here I'm rewriting it in another set of coordinates. So this means that I should find all the solutions of the killing equation inside this. At the level of Y, nothing changes. So if I impose this condition there, the only thing that I found are just the Lorentz transformation, and this makes sense. Because we are far from the sources, we are at infinity, I would like to recover my Poincare symmetry. And so the Lorentz transformation, it's fine. For the Lorentz, for what concern instead the translation, inside this function there are the translations as well, and translation correspond to the situation in which you only keep the first 4 spherical harmonics. Well, I'll write some formula later, but there is much more. So there is an arbitrary function of the angles there, and this transformation with an arbitrary dependence on the angle is called a super translation. It's a generalization of translations. Historically, at the beginning, Bondi and company didn't like it because they wanted Poincare at infinity. When they said, let's try, maybe we made a mistake. It's too, the boundary conditions that we put are not good. But the only way to kill the super translations is to kill the Bondi news as well. So as soon as you have radiation, you must have a super translation symmetry. And the other important things, yeah, I'll gonna sketch is that this is not a redundancy of a description of the system, but it's true asymptotic symmetry. So there is a non-trivial canonical charge which is associated with super translation. So it's a physical symmetry of my system, and the problem is that it's really weird because it's not what we expect. And well, in the following of these classes of GR, you will see a way to relate the super translation to a series of observables in general relativity, and in particular to these things that is memory effect. What is a memory effect is that if I have a wave packet that arrives to infinity, I have some observables that changes with respect to the previous and final configuration. For instance, I have a rotation or a change in the distance between my detectors, and that stays there, and I can measure, and this is a measurable effects of this super translation symmetry, but you will see more later. And what I want to say about the super translation as well. Yeah, now let's see, since this is an important symmetry, it's also a surprising one. Let me try to detail better what super translations are. So here I'm talking about a transformation of this type, which is generated by a vector that takes this particular form. Okay, and very generalized translations in which sense? Because if I take a specific type of T A, which is of this form, so here I have function on the sphere, so I can expand them in spherical harmonics, and I can take just the first 4 spherical harmonics, and the translations associated to the first spherical harmonics, which is the same as picking up the D that satisfy this differential equation. And equal to 0, sorry. This corresponds to ordinary translation. So this looks like a very bizarre way of parameterizing a translation, but this is just because we are in a strange coordinate system. So for instance, something which is clearly a translation, so something generated by this vector, in this coordinate system take this form here, and all this cosine and sines dependence is encoded into the angular dependence of the spherical harmonics. So here really A0 and AM are the constant generators of the translations, and all the angular dependence is hidden inside this one that depends on theta and phi. So, sorry, no, not equal to 0, clearly. And okay, that could be reasonable in the sense that you have this expansion, and this expansion corresponds to the fact that something simple has been rewritten, something which is simple in Cartesian coordinates have been rewritten in strange coordinate system. But why I've written also this one? Because you said, okay, I know what is a spherical harmonics, but the fact is the first 4 satisfy this differential equation. What's okay, is a fact, but why it is interesting? This is interesting because this combination is exactly what pops up in the gauge variation of the metric if I declare that I want to kill also another order in the expansion. So in particular, if I say that the gauge variation is not order R, the gauge variation of a component AB, but is equal to 0, a killing vector, then I get some of these objects transform, and then I get that some of this transformation must be set to 0. But this transformation must be set to 0 are precisely the one that tell me that eventually I only have a killing vector of Minkowski spacetime. And this one I must have, because asymptotically I have Minkowski spacetime, so at least the isometries of Minkowski I have to recover. So the non-trivial information is that just by imposing fall-off, instead of setting them to 0, I get something more with respect to these. And now, just as I anticipated, there will be a discussion of memory effects that is going to follow, but let's try to understand what a super translation is doing. So essentially, instead of doing a translation, in Minkowski spacetime, a symmetry of my spacetime is that I decide to do a translation, so I translate all my solution in one specific direction. Here, what I'm doing is something stranger in the sense that at each point on the sphere, so here the sphere is just a circle, because if you wish, this is Minkowski tree. At each point on the sphere, I decide to do a different translation. So this is, I do a translation which is generated by a T phi du, and this is still a symmetry of my configuration. And in a sense, what I'm doing here is just that I can look, it's maybe a bit clearer what's going on if we look at the final at a finite form of a translation, because the fact that I have a symmetry which is generated by this is just reflecting the fact that I can perform this redefinition of the Bondi metric, essentially, where these terms here are necessary in order to guarantee that this stuff remains a null coordinate. And this is mapping Bondi metric in a completely equivalent Bondi metric, because I just did a redefinition, well, I did just a change of coordinates. It's not that it is equivalent, because there is an asymptotic symmetry and not a true DFO, but formally I just moved from a Bondi metric to another Bondi metric, which keeps the same form. The data in the news, in the mass aspects and all this kind of stuff are reshuffled if I do this transformation, but the form of the metric remains the same. And if I do this, what I'm doing, so at the beginning, remember, I defined my Bondi system just by looking at these null surfaces going to infinity, that essentially I was slicing my null infinity in slices that were all parallel, and I go like this. If I perform a super translation, what I'm doing is that I'm mapping this in a situation in which I'm slicing my null infinity in a different way. But I have a right to slice null infinity as I wish, and this kind of symmetry is just reflecting this fact. But the very strange thing is that I'm slicing it in different ways, but this slicing it in different ways has a physical meaning, because there is an associated charge. And this associated charge is even manifested in some physical effects. And so it's a while that I'm talking about this associated charge, so let me write it. And there is a similar story also for the angular momentum, but I'm going to focus only on the super translation part. And the charge that is associated, that you can compute with the techniques that we discussed yesterday, takes this form here. So here you see directly that I split it in two parts. Why? Because this part here is an exact differential of the stuff, so it's something that I can integrate without any problem. But the other one, you see manifestly that this one I cannot integrate, because if I act with delta on an expression like this, I should get delta NAB, delta CAB. And this means that this is something that I cannot integrate. Even if N and C are related among each other, they are not the same object. So this piece here is not integrable. So the charge is not integrable in this part, but I can use the integrable part, say, to define the Bondi mass. And what the non-integrable part is doing for me is measuring the flux. So the information that now I erased, that I told you that the Bondi mass is a monotonically decreasing function of u, is due to the fact that these kind of objects receive contributions from here, and this is a contribution that depends on the radiation. So if I take the d in dt of this expression, I will get what is usually called a flux balance equation, in the sense that I will have a d in dt of a Bondi mass is equal to something that depends on the time derivative on this object here. And this object here depends on my arbitrary profile that I fix on u for the news, essentially, and is telling me that I have a certain flux of radiation that arriving at infinity, and thanks to the flux of radiation that is arriving at infinity, I have some equation. Well, it's not directly from here, but I have a contribution come from here. I also have a contribution come from here, because if you remember, I have a du of m, which was equal to something. But so this term here plus the other term gives me the measure of the flux that arrive at infinity, and the flux that arrive at infinity has an effect on the charge that I have there. And there is a discussion that you can do also in the case of yeah. And now just a very last sentence, because here I give you the symmetries. I told about super translations, and I told you that if I pick up the first spherical harmonics, all this beast just boils down to the usual Poincaré transformation. But what is the algebra that I have there? What is the algebra of asymptotic symmetries in this particular case? The algebra is the renowned BMS algebra from Bondi, Metzner, and Sachs. And the BMS algebra is nothing but it's almost the algebra of the Lie bracket algebra of this vector. Why I'm saying almost? Because the situation is slightly more complicated in the sense that the formal definition of a BMS algebra is that here I have a y and t. I can just define the BMS algebra as being the semi-direct product of the Lorentz algebra SO13 with the super translations, which means that I can define a bracket of this type, and the bracket between the y's is just the usual Lie bracket of y1 and y2, while the bracket of the t is just given by well, the Lie bracket, I can define something like whatever. So it's YA, DA. That is not so crucial. I can give it plus other terms, otherwise I don't have the time to discuss it. So this is by definition the BMS4 algebra, and I can think that the group associated to it is the semi-direct product of SO13, semi-direct product with essentially R, which are the super translations that are free functions of there. Well, let's call it super translation S. And I can reproduce this algebra just by computing, even before entering in all the problems with the charges. I can compute this algebra starting from the killing vector that I found, but the killing vector are field dependent, and so just computing a killing, the Lie bracket of two killing vectors does not suffice. But what I have to do, this is another subtlety that enters in this context of killing of asymptotic symmetries. I have to compute the bracket using this object that by now is called the Barnich-Troissard bracket, because it's been proposed by this gentleman in 2010, and it's just the usual Lie bracket corrected by these two terms. And these two terms, what they do, they just measure the variation of, they take into account the variation of Xi2 that is induced by a variation of a metric induced by Xi1. Since my fields there have a dependence, depend also on, say, on the quantities that I have into the game, I have to take into account this particular situation there if I want to completely reconstruct the Lie algebra. This is not, and this is due to the fact that there were some order plus order something else, and in the order to r to the -1, there were hidden some dependence on the news and this kind of function there. Okay, so my time is over, but at least you know what are the super translation by now. So let's.
Okay, thanks a lot, Andrea. So, as you understand, Andrea is about to leave, and the GR class will continue with Carlo along similar lines. So maybe, exceptionally, if you want to take the occasion to ask a few questions, just a few minutes, because he won't be here for the Q&A session today. So. Carlo.
What is the effect of a super translation on a black hole?
Well, it gives you another metric that in the past was considered to be equivalent, but now, strictly speaking, it is not. So there have been all the discussion of super translation errors on black hole. At some point, Hawking and collaborators wanted to use them to explain the super, to even explain the information paradox loss. So that is probably too much, but the thing is that some very basic results must be a bit rediscussed, and in general you can ask the same question even for the vacuum. And actually, this is true. So this is something that, so one thing that I should have done, but I didn't have time.
Sorry, the vacuum is not super translation in life.
No, in the sense that you can have a situation in which you have a vacuum, something happens and you go back to the vacuum, but the two vacua before and after are related by a supertranslation, but that is related to memory effects, because this means that there is no radiation anymore. Consider it just a scattering experiment. So nothing happens, say no black holes, nothing static is there. So you have radiation that arrives, does some mess, and radiation goes out, but at late time, you don't have anything more, and but your detector changes, and the changing in the detector is encoded in the supertranslation stuff. It's like saying that supertranslation is moving, people say, from one vacua to another. You have a degeneracy in the vacua, in a sense. And similarly, even if you have a static solution, you can have, say, the same situation where there is the vacuum. So there is a black hole that is stay there, and the scattering is going on. The black hole is changing, essentially. And because there is a non-trivial charge associated to this. And another thing that I didn't have time to make into account is that the super translations leave the Bondi mass invariant, so which means that is a degeneracy of a vacuum in the sense that all the vacua are vacua, they have all the same energy, but they are different because they are related by a super translation symmetry. And if you take the viewpoint that everything that has a non-trivial charge is really a physical observable, then they are really different vacua. And then you may say, okay, come on, but this definition is formal, I don't care, I just want to see something that I can touch. Then a priori these are these memory effects that really tell you that the vacua is different, because the vacua in a sense is not just empty, but it must be defined by a network of observer that stays at infinity, and this network of observer is changed because they are stretched. So before they say LISA, in the space, after the radiation pass, the position of the satellites changes a little bit and remain changed. There is a sort of zero-order DC effect inside this kind of stuff. Yeah.
I noticed that you said that the Bondi mass is decreasing with time.
Yes.
And I noticed that if you consider also the Einstein equation, the differential equation of the Bondi mass aspect, this means also that if you work in linearized gravity, and you can consider the second term on the right side, it means that also C and AB could be decreasing with time, maybe.
No, CAB is completely free up to this subtlety on the initial data, initial characteristic data.
To the derivative of the Bondi mass aspect.
Well, it's better to see the other way around, because CAB is really the initial data that you fix, and then this fixes the time evolution of a Bondi mass. But you notice correctly that is the equations that I've written, if I didn't do any mistake, also is a linear term, which makes sense, because this means that you must see the effect even in linearized gravity, because in linearized gravity you do have radiation that arrives at infinity, so this decreasing of Bondi mass must be there, also there. Yes.
You integrate over the sphere.
Yes.
And then it means that since n is related to CAB, it means that also CAB has to be decreasing, I guess, with time.
Well, no, not sure, no, because this is just the initial data of your differential equation. So if you solve the differential equation, you do not put any constraint on your initial data. So it depends on the structure of differential equation. No? I mean, it's true that it seems that you see du of this stuff, and du is decreasing, but yeah, it's decreasing if you have all the integral. Okay, we can discuss, but there you have an integral, you have a differential equation with some, say, initial data that you fix for your differential equation, so it shouldn't be the case, but yeah, okay, I have to think about it, how to solve this apparent contradiction, but well, unless it's not so direct. Yeah, but for sure the Bondi mass is not a constant also in the linearized theory, because it satisfies this kind of evolution equation. And then, yeah, maybe you have to take another derivative. You see that, that the news is going to zero, disappear, or whatever. No? Because if you want to have to see the evolution of CAB, you take maybe a derivative in u of CAB, and then you may discover that the part that is relevant to that equation just disappear. I think it's something like that, probably. Okay, I don't. Okay, I have to look at the details, but it should be there. But that is at least it was a good remark in the sense. Well, it triggers another remark: is the fact that the Bondi mass has also a linear term, the differential equation that roots it, but also non-linear ones. So you really see that the fact that you have interactions make an effect into the system. But why? Because the self-interaction of the gravitational fields has an effect also on the energy that you see. So are really important in the details of the problem. They are important in these flux balance equations, essentially.
Okay, maybe
So,
one last question, if any. In any case, we will have the Q&A session also with the gravitational part. It's a bit strange because you can ask questions to Carlo, although his lecture will start later.
but
But I mean, it can be nice anyway. You can ask general question and let's see how the discussion evolves. Okay, so in the absence of additional questions for Andrea, we thank him again.
thank you.
And let's say